Hello, welcome to our class in computational science. This is a first class in computational science, or maybe a second class in scientific computing. Today's visit here in my office will be fairly simple. We'll just introduce ourselves, introduce what we try to do, and then send you off to work. My name is Rubin Landau. I'm a professor of physics at Oregon State University, and I've been a computational physicist since I was in graduate school. Now, recently, I head the Computational Physics program for undergraduates here at Oregon State University, and that's a BS degree program and started fairly recently. Behind the camera, who you usually won't see very much of, is another computational scientist, Sally Hare. She's coming here right now to say hello, and she's been working for many years as well in computational science. Sally acts as our director, our editor, and our producer.
Well, hello, and I welcome you also to this class. I will be doing the work behind the camera, and I'm excited about this opportunity for you to listen to a class from another in a totally different venue, and be evaluating how this works, and I will be very interested in your feedback and your comments. So as we go along, please let us know how it's going. And now I will go back to my little place behind the camera. I'll be watching you through the class.
Thank you, Sally. We also should say thanks to Oregon State University, who supported this project in various ways, to the National Science Foundation, who supported this project in a number of ways, particularly supported the books that this project is based on, and to EPICS, the Engaging People in Cyber Infrastructure program, also supported by the National Science Foundation, who got us going. Okay, so let's move on. And this, I have to sort of apologize on this slide. This is our Department of Shameless Commerce slide. You won't see this too often again. But what is this class about? Well, computational science is really about how to use computers to do science or engineering, how to solve problems with computers. And that's what we try to teach. It's the second course because we assume you know your way around the keyboard. We assume you know a little bit about operating systems, about shells, about running software. We also assume that you've learned someplace in your career, or you'll learn on your own very quickly, how to run compiled languages. This course is predominantly focused, at least when we speak about it here, on using Java. Other compiled languages are okay. We'll talk more about that shortly. So, if you haven't had it already, a first course in scientific computing, there's a book, not a bad book I must admit, out there published a couple of years ago that tries to teach you how to get around the keyboard, how to use compiled languages, how to use symbolic languages, and that's published by Princeton University Press. We assume you know that. You can buy it online. Buy one for your parents even. Okay. This course follows that. And it's preliminary course in its own right, as we'll see, to a truly specific course in computational science, what we often call computational X. X could be physics, which is what we predominantly talk about when we move on anyway. X could be biology, could be finance, it could be genetics, could be anything. Okay, so that's still to come. We won't cover that here. What we will cover are these lectures, and they're all based on materials from this brand new book, A Survey of Computational Physics. So it's a new book, just came out recently, coming out in 2008, also printed by Princeton University Press, and it has my co-authors who deserve some credit, Manuel, Paez, and Cristian Bordeianu. Okay, so those are the subjects. So now we'll move on to slide 3. What is slide 3 about? Take a look at it. How do you use these lectures? Okay, so these are video lectures with PowerPoints. And as always with lectures, one has a choice. You can view them after you read the book, then you read the book. You might just survey the book so you have some idea what's coming. You can use the lectures to give you a good idea what's in the book, and then read the book after you've heard the lectures. Or best yet, do both. That's what I recommend. In any case, I recommend reading the book, not just our book, but anytime you have a book to accompany lectures, because there's usually much more in the book than we can put in the lectures. And there's more details, but the lectures are also a lot less formal. We try to just get the big points across and the concepts. So that's what we try to do in these lectures. As you're seeing me now, presumably, you're looking inside a web browser. These movies can be viewed various ways. We've made it very simple by having a Flash-enabled web browser. Most browsers that you have now are Flash-enabled. So you're seeing me here in this little window as we speak, okay? And that's easy. We've done this for a number of reasons. One of the reasons is these lectures you can view, you can listen to, you can take anywhere. You can even podcast them, although then you probably want a smaller version that'll fit on. And you can look at them many times. You may not want to look at us many times, but you certainly have that option. What you see here, and presumably it's right below me down here someplace, is a table of contents. So this is what we are covering in each lecture. And you have the option of clicking on this table of contents and jumping any place in the lecture you want. So if you have to come back or take a break, or you've heard enough of us for a while, you can stop the lecture. There are controls right below, down here, that let you stop the lecture, start it, pause, start from the beginning, etc. So you have total control. It's free. You can look at it as many times as you want. You can jump around, repeat a section, repeat whatever you want. At some point, you may get tired of my voice. That's okay. I mean, we're trying to teach you something here, but it may not be okay for other people who aren't learning anything. So we strongly recommend that you use headphones when you listen to these, particularly if you listen to them in a laboratory setting. If you need to control the volume, often it's at the bottom of your screen. It's someplace on your computer. This image you're looking at, this web page, which has the movie here, it has PowerPoint slides on the side, it has us talking to you, has other items on it. Each one differs. So what you'll find on the bottom is you'll find links. And this will be links either to our web page, could be a local web page, could be links to what might appear on a CD or a DVD someplace. But if you look at this on the web, these are links to actual programs that accompany the textbook, applets in some cases, color animations, visualizations, other items. And all this material can be customized to your local class, so it may vary somewhat. But we encourage you to use it all. If you haven't realized it already, you will soon. What we're trying to do here is give a lecture much like a lecture you'd see in a class. It is not scripted. In other words, we don't know exactly what we're going to say. Even though we've planned it very carefully, we know what items we want to cover, we know what materials to include, what to leave out. But we have found, Sally and I here, where we did surveys and some students, listening to a scripted lecture is kind of boring. It's very much like listening to a newsreader on television. They sound great, but they often have no first-hand experience with the material. They often, sometimes anyway, don't know what they're saying, what they're talking about, but it sounds very good. Here, we know what we're talking about. We've done this material. We may make mistakes in our language. We may repeat stuff, but that's what the real world is like. So this is much more realistic. Let's hope it's not nearly as boring as it might be otherwise. Finally, we should say these slides are accessible to disabled people in various ways. We have, of course, sound. We have vision. If those of you who need something else, need more hands-on approach, we also have LaTeX versions of the slides, which can be read by even the equations can be read by a reader. Or if you need the PowerPoint slides themselves for accessibility, just contact us, contact me, my webpage, there's an address, and that should help. One use of these lectures, one we encourage, is to have the students, have you, listen to these lectures, and then have more time to be in the laboratory with your professors, with your instructors. And that's using distance education technology, which is developed by many, many people, using that to decrease the distance between you and your education and your instructors. So let's look now at slide 4. And in slide 4 we'll talk about the philosophy of the course, the philosophy of the lectures, and some details about your local setup. Well, if you haven't gathered it already by our introduction, the attitude I have, the attitude in the lectures, and we try to transmit them in the book, is that the best way to learn computation is by doing it. And the best way to learn computation is while you do it. You just can't beat sitting down at a computer and computing while you're trying to understand how to compute something. Okay? And that's what we try to teach you here. We not only try to teach you how to compute, but we realize that this mechanism of computing, trying to solve scientific problems on the computer, is a very good motivation for you to learn more science, a very good motivation for you to learn more mathematics. In fact, the understanding of science and mathematics in depth often is as great or greater than you get in any place other than in a research environment. One of the things we try to teach, indirectly anyway, is how to be creative with the computer. Indirectly in the sense, we don't tell you everything to do. You can learn on your own very well, and you learn better than we can teach you how to do things that work for you. So we'll have practical applications, and you'll work through them. That's the way you really learn. Here it's nice to listen, but you really learn by doing it. As you can tell, this is not the theory of scientific computation. That might be appropriate for a graduate level course where you know how to compute and you need to know the background behind everything. We want you to do it. Up until recent times, within this time we started this program, in fact, last 10 years, it was held in the scientific community that undergraduates should view computation as black boxes. So there's the black box, okay? They shouldn't know what goes on inside the black box. They should just let the computer take care of things. Well, that may have been true a decade or so ago, but now computing so permeates all of science and engineering that it's valuable to know what goes on inside the blocks. So we try to get your hands dirty, get inside the black box, and make you do things and follow it. And it's fun. One of the ways we do that is our emphasis here on compiled languages. Okay? Rather than just using a package or a complete studio environment, although they work very well, we want you to get closer to the algorithms, closer to the mathematics. And by doing that, you put all the pieces together, and then you get the confidence, oh, I can do this myself. I don't need somebody else to do it for me. That's what we'd like to teach. Presumably, you've all done some coding in your life. And coding is very rewarding. The logic of it is very satisfying. The fact that you're completely in command, you're making the computer do everything you want just by writing these little commands, that's great. The problem is it's hard to debug. And the debugs are boring, and it spends lots of time. It takes lots of time to do that. So we've tried to compromise here. We don't discourage you from writing your own programs, but in order to save time, we give you sample codes. They're on the CD that accompanies the text. They're probably on a website as well. And hopefully that gives you more time to explore using these codes, because they're not meant to be complete. You should extend them. You should explore with them, try new things, break them if you can, but at least get started. It's much easier to have a running code and build up than it is to start from scratch. It's also very realistic. The work environment hardly ever gives you the chance to write your own codes completely from scratch. They want you to use something that's there. This is a good way to learn. As you might tell, to do all this, you just can't use a laptop that you pull out of a box someplace. So here, maybe if you're an instructor, or if you're trying to do this at home, is a bunch of the software that we recommend. The good thing about this is essentially all the software is free. You can get it on the web, you can run it at home, Unix, Windows, most of it, we talk about that in the book, you can run at various places. So we recommend having a loaded computer, a computer lab, someplace you can run your programs, play, explore, and work on the projects. Projects are essential because you do the projects, they become yours, it's your own investigation. You're not doing homework for me or for some instructor. You're trying to solve something on your own, learn about it, and that's the best education we can give you. What do we expect you to learn? We expect you to know how to compute, we expect you to know how to compile and to understand what you're doing. What you'll need to do that is the Java Development Kit. You can get this free from Sun. The essential thing here is you have to have a compiler. Most browsers, most computers are Java enabled, but they run Java, they don't compile it. You need to compile it. That's all free. We prefer that you run Java, you compile it from a shell, so you do it by commands. You actually give commands. You know the different types of files. You know what they're there. You don't have 100 files, just have 1 or 2. That's, for us, the best way. Other people may want to use a studio environment. That works, but we recommend that. By the way, lots of talk about Java as a language. Java is excellent, we have found, for this course, for the whole undergraduate experience. It's universal. It's the same on every computer. It's free. It has a very good interface and commands, error messages for scientific computing. It's very careful with its use of precision. You can't mix different kinds of precision. You have to know what you're doing. The security is very good. You can't get into harm's way like you can with C, which is more powerful, but lets you get places you shouldn't be. It's very good for us, and it runs more than fast enough now for all the projects we'll give you. However, if you go on to research, and this course is designed for undergraduates, many graduate students take it. Once you get on to research, I recommend that you move to one of the other compiled languages, either C or C++, or Fortran 95. They're also object-oriented like Java. They can run 10, 30 times faster. They're not free. The compilers vary. They're not as universal at all. But that's where high-performance computing is done. And on the codes, on the CD with the book, shameless commerce will end soon, I guess. With the book are actually codes in C and Fortran 95. So even though you may be taking the course in Java, you may at times want to, may have to, try a C code, try a Fortran code, and then it's not that hard. The ideas are the same regardless of the language. We recommend various visualization software. GNU-Plot is excellent, runs on everything. AceGR is the best software we know for producing scientific plotting. It's free. It only runs under Unix or Linux, but you can run it under a Cygwin window on Windows machines. PTPlot runs every place under Java. We build it into a number of the codes. It's very good. OpenDX, formerly IBM Data Explorer, that's what DX is, Data Explorer, is also free. It's now open software. It's a little bit high-end for beginners, but it is industrial strength. And finally, JAMA, which is just matrix library. Any matrix mathematical library is very good for you to learn how to use. Various editors, whatever you want. JEdit is very good. Java editor, written in Java, runs the same on every machine. Learn how to use shells. Emacs is also a good editor. Okay. Some of the things your instructor will have to worry about, or you'll have to organize, is when you'll be taking these lectures. You can take them any place you want as far as we're concerned, more better. Where you'll be going to the lab, when you'll meet, where you'll meet, which computers you'll be using, because as I said, you can't just use every computer. You have to have one that's equipped to work. There are assignments. We won't assign too many assignments in class. We'll talk about some here, but we'll leave that up to your instructor. It's one way of customizing the course. Likewise, the exams, that'll be something you'll have to figure out locally. If you want tips, if you want to see how we did it, you can certainly look at the links on my page and see how we've put the pieces together. Okay. So now let's get on. Enough of the logistics. Let's talk about the nature of computational science. Well, the word paradigm shift has been used so often, it sort of is a bore, and it doesn't mean anything much for everybody anymore. However, this was a true paradigm shift in the last decade or so in how science is done. It used to be, and my training was as a theoretical physicist, and that's all there was, and then there was experiment, and those are the paths we had to follow in order to find truth. Well, it's changed now. Simulation or computation, very similar words, simulation now is recognized as one of the pillars, one of the founding corners of scientific research. It's all mixed together now. Both in experimental and theoretical work, simulation comes in. This is very important for your education. It's very important for the future. What we'd like to teach you in a course such as this is how to explore the models that you take of the real world, of science or engineering, and how you use them on the computer to solve problems. When you do that, you'll understand some of this material at a greater depth than might otherwise be possible. And that's not just true for you as a student, that's true for everyone, scientists, engineers working in the field as well. This is a great freedom we haven't had before. Some of the problems we'll look at are ones that are too difficult or too complex that have even been looked at before. So these are problems which are either beyond analytic solution, or the analytic solution is so complicated and messy it's completely unilluminating, and yet the numerical solution is very simple to look at. Or these are problems which are just beyond human endurance. They're just so complicated you wouldn't want to become a person who can do it. Okay? On the computer it becomes easier. So what is the computer? Well, we use the computer for many different things. We use it for many cases, as the obvious one is just a supercalculating machine. It can do a lot more things more quickly than you want to. It's also a laboratory. It's an environment, a simulated laboratory where we can look at the world. So these models are not meant to be just purely abstract mathematical models. They're meant to represent something in the real world. It's also an intellectual lever. Okay, so we can do things which we could think about but not be able to do with our limited brains. That's also what the computer is. And ideally, it's all three. Okay? So what is computational science? We talked about what we're going to do. Well, computational science is one of these multidisciplinary subjects. Okay? And I use the term here multidisciplinary rather than interdisciplinary, because an interdisciplinary might fall between the cracks. Multidisciplinary means that we have several subjects and you need to know about all of them. Okay? So we'll use the abbreviation CX sometimes, or CSE, computational science and engineering. That's very popular in the literature. CX for computational, X being your favorite. So here we could say, for example, computational physics, my own specialty, is what? Well, it's a combination of science, in this case, application, as a CS person might say, physics. It's application of computer science, which is the hardware and the software, and it's a combination of applied mathematics, where the techniques come. So this Venn-like diagram, it used to be, maybe when it was considered interdisciplinary, sort of the overlap of all three, but now we realize, no, it's some of all three, but there's also its own field. There's also a bridge that draws it all together. And one of the very nice thing about computational science is that since its focus is on scientific problems being solved with computers, and the techniques, the philosophy, the methods, the toolkits are the same for all the different X's. Okay? So even though we might be talking about physics, in fact the approach to solve a problem we'll be using is very much the same as used in engineering, mechanical, maybe used in biology. And so there's a commonality of techniques which let us work in other fields, make us switch to other fields very easily, let us understand other fields. So this is in marked contrast and pleasant contrast to sort of this super sub-specialization which pervades so much of science and makes it very hard for you to move out of your small niche in the world. Computational science is freedom. Okay? You can do much more. What about computer science? Okay? Well, computer science, often abbreviated CS, is a different kind of subject. It has its own focus, mainly on computing for its own intrinsic interest, developing the hardware and software tools one needs to do computing. It's a strong field. These are valid, very important for us, content of computer science, but we're not computer scientists. We don't try to teach computer science per se. We have a very different outlook and attitude. And it's not just semantics, okay? It's not just semantics. You know, the difference in focus is quite real. Likewise, the difference in how you'll be judged, the difference in what we're looking for you to understand will be very different. One One well-known computational physicist, whose name I won't mention, said, well, the difference is that if you're a computational scientist, you have to solve tomorrow's problems with yesterday's computers. Whereas if you're a computer scientist, you sort of do it the other way around. Think about it. Okay. How do we organize all the material we give you in the book? How do we organize all the material in the course? Well, in keeping with this computational science problem-solving viewpoint, we employ the problem-solving paradigm. So we want to look inside the black box, and when you do that, you look, oh, well, if we're solving a problem, we do it scientifically, the scientific model. We first try to tell you what the problem is, and for an elementary class like this, the problems tend to be very simple, by and large, but at least you realize that's what you're trying to do. How do you solve a problem? Well, you start with maybe a theory. Theories are often too complete, too hard. You simplify the theory, you make it into a model. Or sometimes you don't even have a theory, you just start with some model. So you know it's not a perfect description of nature, but it's an approximation. And that's fine. You know, that's how science is really done. The model could be discrete. Computer models are almost always discrete, or it could be continuous, which analytic, symbolic models may be. The method we use could be numeric or symbolic. We tend to focus on the numeric here, but we could do a lot of this symbolically as well. Then we talk about the implementation. Once you know how you're solving it, you know what algorithm you're using, then you can talk about, let's write a program to do it. That's a fancy word for implementation. Okay? We tend to be Java, it could be Fortran, it could be C. At all stages, we will look at assessment. Okay, so this is also, assessment is sort of a catchword now in many areas of education, but we mean it in the sense of, am I doing the right thing? Is it working? Did I make the right choices? And it's not a criticism, particularly on the computer. Whenever you write something, you tend to make a mistake. So you always have to be checking. You learn to check, then you know at the end you've checked enough, you know the problems have been dissipated or they're not so big. The way you do assessment is particularly with visualization and also then by exploring items. And if you notice here, this arrow with assessment goes at all stages. So in the years past, you know, when I was first learning computing, we'd only do visualization at the last step in the process. Now, do it all the time. If you can use visualization to debug a program, that's a much faster and easier way than just looking at reams of output. Okay. So now let's look at slide number 8. There's a lot of information here. This is the course topics. And what you should see here, other than these details, is the course, which we'll talk about now, one term, maybe 10, 12 weeks, covers roughly 1/3 of the textbook. And I have to admit, to me, it's probably not the most interesting third of the textbook because the emphasis is on tools. Okay? Before we get on to the science, in other words, before we get into the X and the specialization where we can talk about the subject matter of science, we need to know tools. We need to have the language down. Okay? Landau's first rule of education is most of education is just learning the language. The ideas are quite simple. We need to learn the language. But it's also a good thing for us here because this course then can be used as the first course for many different subjects, many different X's. Okay? So what will we talk about? We'll talk about introduction to computational science, the computational basics. We'll talk about errors and uncertainties in computation. Very important. It doesn't mean because you're error prone, it means the computer is error prone. You have to know how to handle that. We'll talk about trial and search errors. You've heard probably about, you know, many times people say, well, to do it by trial and error, you may not want to think a lot of computation is done that way. It is. Okay, and it's a fun way to do it. Visualization, object-oriented programming, computer science topics, critical for much of science. Monte Carlo simulations, that's great. That's at least real science. It's not just a tool. It is how we do tools. We'll talk about matrix computing, linear algebra, using scientific libraries. We may not, depending on the course, as you've set it out, learn about computer hardware and tuning. Computer hardware is something I recommend you read about in the book right now, right at the beginning of the course, if you know nothing about it. We'll cover it in more detail in the course, but it's nice to know how these computers work, and in our experience, very few people, scientists anyway, learn that. Okay, you know, they're just given to you. It's not that hard. Integration, differentiation, this is very important. It's the basics. It helps you understand the mathematics of integration, differentiation, maybe better than you ever have before. Data fitting can't be beat. It's a great topic. We should spend a year on it. Maybe you can talk somebody else into it. And we'll end off, at least the first term, talking about how you solve ordinary differential equations on the computer. It's easy, it's fun, and it works all the time. So do it. Here on the last slide, really, we have a big overview of everything we're going to learn. This is known as a concept map. It's a way of looking at what might be called a field of knowledge with the different connections between them. And obviously we've cut down on the different connections here just to make things a little clearer and not to have spaghetti all over the place. But what you can see here is a few things. You can see, okay, there's the math we talked about, here's the science in a general sense, and over here is the CS you're going to learn. Hardware and software in CS, the math is numerics, the science is called applications. That's the computer science word for science. And what you see with the red dots are roughly the subjects we'll talk about in this course. So you see it covers, it may look like more than 1/3, but that in part is because you get onto the more advanced topics, we have to slow down a bit. And you'll see, oh, they are very much interconnected. You can't solve differential equations until you know a little bit about derivatives. You can't do trial and error searching by itself without learning about matrices, because the problems end up with many equations to solve. But the more you use the tools, the rest gets easier. So this is what we'll be looking at in the future. It's probably not clear to you now. If it scares you, that's good. Okay? That means that at some point you'll look back at this and say, I used to be scared of that when it really was so easy. I love those topics. I want to learn more about them. So that's goodbye for now. I think it's time to move on. Let's get to work and learn some of that subject matter. See you soon, I hope.